Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads determine the moment of inertia of the shaded area about the y-axis as well as the x-axis. This problem is coming from the engineering mechanics statics textbook 13th edition by R.C. Hibbeler. So we are determining moment of inertia of an area, also called second moment of area, and also called area moment of inertia. So it can be called moment of inertia of an area, or area moment of inertia, or second moment of area. Okay, they all mean the same thing. So what is this moment of inertia of an area? This is a geometric property of a shape, such as a cross section of a beam, that describes how the area of that given shape is distributed around the chosen axis, that axis that we want to determine the moment of inertia about. Right, and it has so many applications, some of which in structural engineering we use it to calculate the deflections of beams. We use it for buckling load calculations of columns and many other applications. Mathematically, moment of inertia about the x-axis is equal to integral of y squared dA, and moment of inertia about the y-axis is integral of x squared dA. Alright, earlier on I did mention that taking a strip parallel to the axis is much easier. Alright, remember I did mention that taking a strip parallel to if I wanted to find moment of inertia about the x-axis, I said we have to take a strip that is parallel, remember? But sometimes, most of the times that works. But for this particular problem, it is better to take a strip that is perpendicular, not parallel. Why? Because if we were to take a strip, this strip that is parallel to the x-axis, and we want to find moment of inertia about the x-axis ix, which is integral of y squared dA. Alright, if we did so we are going to be integrating along the y-axis. But the thing here is, when we look at the function that governs the curve, it starts from this point. You see this point? So it means we have what? Two areas here. We have this area at the bottom, which is just basically a square. Then we have another area, which is basically this area here. Now I'm talking about integrating with respect to the y-axis, or with respect to the y. Okay, so if we did so, then we need to employ another method, which is computing moment of inertia for composite areas. Okay, that is, if we are to integrate this with respect to y, with respect, again I repeat, to y. Okay, then we have to use moment of inertia of composite areas. But if we are to integrate this with respect to x, we don't have to do that. Alright, we can still work out or find moment of inertia if we integrated with respect to y, but it would take more time. Okay, but if we integrated this area to find moment of inertia about if we integrated with respect to x, it would take less time. That is basically what I'm saying. Okay, and we want to choose the method that takes much less time. So instead of choosing a strip that is parallel, like I've always advised, which works most of the time, but for certain functions it will not always work. It will work in a certain axis better than the other one. All right, or integrating with a certain variable better than the other one. So for this one, the one that works best is taking a strip that is perpendicular to the x-axis. Okay, so this is what we are going to do. So this is our dx, okay, and it intersects the curve at this point, which is our x comma y, and therefore this length here from there to there, this is our x, and then this is going to be our y, and then we have the centroid location of this part, which is equal to y curled equal to y over 2, which is also equal to dy. Okay, so let's call this axis that is passing through the centroid of this small strip as our x prime. So for a problem like this, where we want to find moment of inertia about the x-axis, and then we have this small strip whose centroidal axis is parallel to the axis where we want to find moment of inertia, then we have to employ the parallel axis theorem. Okay, before I describe mathematically what the parallel axis theorem is, let me define our dA. Our dA here is just going to be equal to our height, which is y, times the thickness, which is dx. So parallel axis theorem is Ix is equal to Ix prime plus dy squared, okay, times the area. Writing this as differential moments of inertia, we'll have dix is equal to dix prime, okay, dix prime plus y curled squared dA. So integrating on both sides so that we write this, then we'll have our ix is just going to be equal to I think we can write it here, we can extend it here. This is going to be equal to okay, just write it down. Our ix is now going to be equal to, so this strip, remember we already know moment of inertia of a rectangle, right? What is the moment of inertia of a rectangle? Given we have a rectangle like this whose height is h and whose width is b, is what? Bh cubed divided by 12, right? So our b in this particular case here is our dx, our h is our y cubed divided by 12, then of course with an integral there, plus an integral, this y curled is just y over 2 squared, then our dA is just y dx, which is just y dx. All right, so to evaluate this or to simplify this, this is going to be equal to integrating, of course, from 0 to 1, we have y cubed divided by 12 dx plus 1 over 4 y cubed, like so, and then later on we can write this, okay, simplify this, we can multiply both sides by 3, we can multiply there by 3, let me just write this, so we can multiply there by 3, we multiply there by 3, of course we still have our y cubed dx, we simplify this, it will just be equal to, that's 4 divided by 12, which is just 1 over 3, integral from 0 to 1 of y cubed dx. And we know what our y is. Our y is just equal to e to the power x squared. So replacing this there, we are going to have ix is equal to 1 over 3 integral from 0 to 1. We replace it there, it becomes just e to the power 3x squared dx. Alright, so now we need to use the technique that was just recommended to us, which is the Simpson's method. So our function in this case of x is equal to e to the power 3x squared. So integrating using Simpson's rule, integrating from 0 to 1 of this fx dx, this is approximately equal to delta x divided by 3 delta x divided by 3, where we'll have f of x0 plus 4 f of x1 plus 2 f of x 2. We can go on plus another 4 f of x. We can go on, but for in our case we are going to use n is equal to 4. Okay, so I'll just write the full expression for us. So we have 1 2 3, then another one 3, and then plus f of x x4. So our delta x is equal to a b minus a divided by n, which is equal to 1 minus 0 divided by 4. We said let our n equal to 4, and this is just a number of even subdivisions. Okay, they are supposed to be even. Okay, and b and a, these are just the constants, see, over which we are supposed to find the area under the curve. So we are dividing the area under the curve into a number of even subdivisions, and then later on we sum up those areas of each subdivision to find an approximate area under the curve. So this is what this method is doing. So you have a curve, and then you have some area from B to A. So and then you subdivide this area into a number of even subdivisions. Okay, so you have 1 subdivision, 2, 3, 4, and then you sum up these subdivisions. The more the subdivisions, the more the solution becomes accurate. So this is what this method does. Simpson's method of approximating definite integrals. Okay, so it's an approximate method of finding an approximate solution for definite integrals. Okay, you can check it out for more details. All right, so this gives us a 0.25. So this is the width of each subdivision, or the width of each strip. We can think of these subdivision as strips. Okay, so if I was to show this on the number line, we are integrating from 0 to 1, and we've subdivided that into 4 subdivisions, and the thickness of each subdivision is 0.25. So from 0 we move to 0.25, then later on to 0.5, then to 0.75, then finally to 1. So this first value is our x0, this second value is our x1, x2, x3, x4. Okay, so finally we have our ix which is equal to integral from 0 to 1 of integral from 0 to 1. What was our expression? This is 1 over 3 out there, e to the power of e to the power of 3x squared dx. So we have a 1 over 3, you don't need to forget that. Then what did we say? We have our dx, delta x rather. What is our delta x? Is 0.25 divided by 3. Then later on we start now plugging in these functions. F of x0, what is our 0? Our x0, it is 0. So it is e, the function is e to the power 3 times 0 to the power 2. That's our first term. The second term, so we have these values that repeats 4 and 2. The first term has no value before it or no coefficient. Then the next ones, they will have these 4 2 4 2 repeating. Okay, depending on the number of n that you've chosen, and n has to be even always. Okay, so e to the power 3 0 squared, e to the power 3 times 0 squared. Then the next one we said is 4 e to the power 3, then 0.25 squared, then plus 2e to the power 3.5 squared, plus the next term, which is a 4 e to the power 3 by 0.75 squared, then plus e, the last term hasn't got anything, also the last term. So the first term and the last term, nothing, but the terms in between is 4 2 4 2 4 2 and so on, depending on the value of n, and n is supposed to be even. Then we have 3 to the 3 1 to the power 2, like so. Then we close the bracket. Okay, so here I need to make sure that I indicate this is an approximation. So this therefore gives us an approximation of, if we are to do the calculation for this one, work out those values, we are going to get a 1.438. Okay, so for n equal to 4 subdivisions, where our delta was equal to what was our delta? 0.25. We found that Ix is approximately equal to 1.4380. Okay, so I went further to say, let me change the value of n. I increase it. So when we increase the value of n, we increase the accuracy, right? So I said, let my n, at least, I know this is cumbersome, and if you had a problem like this and they specify what method to use, I know your professor will specify the number of subdivisions, the value of n that we are supposed to use, because the more the values, the higher the value of n, the more tedious it is. It's very tedious. So n is equal to 10. That's what I did, and then my thickness of my strips was 1. That is 1 minus 0. So 1 minus 0 divided by 10, which is 0.1. So this was 0.1. This was the size of the strips. And then finally, when I did so, I was able to get the following. The solution became the following. When I did this, it was equal to, where is my pen? There we go. My Ix was equal to, approximately equal to 1.4085. I ended here at n is equal to 10 because it was laborious, and this was a good approximation. Okay, so basically this is the value that we are going to take, which is moment of inertia about the x-axis. So now let's go to moment of inertia about the y-axis. So moment of inertia about the y-axis is equal to integral of x squared dA and we already have the dA. Okay, dA we are going to be integrating with respect to x, so the integration constants are the same from 0 to 1. So x squared, our dA is just y dx, and we know what y is, right? What is our y? Our y is equal to e to the power x squared. So integral from 0 to 1 x squared and then e to the power x squared, like so, dx. So our function therefore that we are dealing with now is equal to x squared e to the power x squared. This is our function. So applying the same technique, which is the Simpson's method, so I had to take n equal to 10 here directly, which I'll not show, and our dx, which is the size of the strips, was 0.1. So when I did so, I found that my moment of inertia about the y-axis was equal to moment of inertia about the y-axis was equal to 0.6279. Okay, approximately again. Okay, let me. All right. So we can now finally say our moment about the x-axis is approximately equal to 1.408185, and then moment of inertia about the y-axis is approximately equal to 0.6279. Both of these, they are in meters to the power 4, meters to the power 4. So this is about it. And I hope the video was helpful. If it was, give me a thumbs up, like my video, and follow the other video that I've done on moment of inertia. I've included the link. Bye bye, and see you in my next screencast.